Okay, so here we go with the free response questions. This is take 2 on this video. So here we go. On number 1A, we're supposed to circle the one that best represents what's happening in that bond between phosphorus and chlorine. Covalent bond between phosphorus and chlorine. And they're showing us one that has phosphorus with the partial positive and chlorine with partial negative. And the other one, phosphorus is partial negative and chlorine is partial positive. What you got to remember is, let me scroll down here, the partial negative on the more electronegative element. So which is more electronegative, phosphorus or sulfur? Obviously it is, phosphorus or chlorine, not sulfur. Phosphorus and chlorine. Chlorine is more electronegative than phosphorus. So we will circle the one that has phosphorus as being partial positive and chlorine as partial negative. And so that's the one we're circling. We have to justify that, and to justify we say the partial negative on the more electronegative element and chlorine. We can use the periodic trends on this. Chlorine is more electronegative. Oops. Because it's farther to the right. Letter C, we're going to circle one, and we've got oxygen and selenium. And oxygen and selenium are in the same column on the periodic table, but oxygen is nearer the top. So we're going to put the one where oxygen is more negative. And the reason we're circling that one to justify oxygen is more electronegative because it's higher in the group. On the periodic table. Remember, we can only do that because in the directions or in the question it says you can justify using periodic trends. We can use the periodic trend on this one. Most of the time they don't let us do that. Letter E, we've got greatest dipole moment. The greatest dipole moment will be the ones that are the farthest apart on the table. And they're all three connected to O. So which is farther from O, carbon, germanium, or nitrogen? It's clearly germanium. That's the one we're going to circle. Because GE being farthest from fluorine is least electronegative. Of the three. So it has the greater dipole. Letter G. We are circling the one that has a dipole moment of 0. The only way to be 0 is if the two elements are exactly the same. We're circling C, C. And it did not ask for us to justify. And if you are in second period and you did this live with me on Thursday, I gave you the wrong answer there. It should have been the C-C. But I'm having trouble seeing, so I'm using that as an excuse. I'm going to milk that for everything I can. So there's some more keys there, the bullet points that will help you in figuring out questions like these. All right, next page. We got this nice graph. It shows the bromine and chlorine. And it asks in 2A, what is the distance, or the bond length for the BR-BR bond? The bond length in the BR-BR bond, I go right here. It's about 225 picometers. Second period on Thursday, I read the question wrong. It said, what is the bond energy for BR-BR? And I had read it thinking it was wanting the internuclear distance on the chlorine-chlorine. So I got that one wrong. But fortunately, it is practically, it's just above the negative 200 line. So it's about negative 200 kilojoules per mole. And if you don't put the negative there, that's okay. You can just say about 200 kilojoules per mole, or if it makes you feel better, 198 or 195 or something like that, kilojoules per mole. It's just, negative is saying that the energy is released when the bond forms. So if we want to break that bond, we have to add in that much energy. So whether you put the positive or negative at this point did not matter. Letter B wants to know, do you predict the bond length of the CL-Cl bond should be shorter or longer than that of the BR-BR? I'm going to say that CL-Cl should be shorter. And if you're using Ms. Markstaller terminology, that's my claim. I need evidence or reasoning after that. What I would say is because chlorine being higher on the table has a smaller radius than bromine. So Cl bond should be shorter. Right, because if that radius is smaller, then the distance between the two atoms would be smaller as well. Letter C wants to know about the bond energy. Students sketch a potential energy curve for the two Cl atoms on the diagram above, as indicated by the dotted lines. There's an error in the sketch. Identify the error and explain how it could be fixed. So the error is, right, it should have come down farther. The CL-Cl should be deeper than the BR-BR. Okay. Since the bond is shorter, it will be stronger. And therefore more energy. So a deeper valley, for want of a better word. It's not a peak, it's a valley. Number 3 on the next page says, it gave us a chart there showing the appearance and the melting point of a particular compound. It wants to know, is it SCl or is it CaCl2? Well, what you need to keep in mind here is sulfur and chlorine are both nonmetals, so that makes this a covalent bond and a molecular compound. And the calcium and chlorine, that's a metal and a nonmetal, so this is an ionic bond, which is an ionic compound. And we saw earlier that ionic compounds are crystalline solids at room temperature and have a high melting point. This one is showing up as a red liquid with a very low melting point. For A, I'm going to say SCl is what is demonstrated in the table. That's the one we circle. And for B, justify in terms of the type of bonding present. So we've got SCl is a covalent bond. Making this a molecular compound. You could probably even say covalent compound and they would count that, right? And so it has a very low melting point. If it were the calcium chloride, you could say the opposite. It would be an ionic bond. So it's an ionic compound which would have high melting points, very high melting points. So I think that's enough of an explanation on that. It's a liquid, not a solution. That's a difference. You know, if it was, the calcium chloride will dissolve in water at room temperature, but it is not a liquid until you get above its melting point, which would be pretty high, probably over 1,000, I would guess. Okay, so that's number 3. Number 4, they gave us a drawing that looks something like this. And wants us to draw C2H2, which C2H2 would have 10 valence electrons, 4 for each carbon for a total of 8, and 1 for each hydrogen for a total of 2 more, so 8 plus 2 is 10. So there's 2, 4, 6. I've got 4 left to go. I can't put any more on the hydrogens. If I put 2 on each carbon, that doesn't give you an octet. If I put 4 on one of the carbons, the other one doesn't have an octet. So we can't do this by just placing lone pairs. We're going to have to add more bonds. This turns out to be a triple bond in order to get all 10 electrons. Okay, so there's the drawing. That is letter 4A. It says that this bond here has an energy of, what, 350? 350 kilojoules per mole. And it wants to know about this one, higher or lower than 350. So being a triple bond, it's going to be a much shorter bond, and shorter bonds are stronger. So since C2H2, the carbon-carbon bond is a triple bond, it will take more energy, so it has a higher bond energy than in the other one. And we'll need to say, our claim is then C, triple bond C is greater than 350 kilojoules per mole because the triple bond has higher bond energy. It's also shorter. And as we saw earlier, shorter means more energy. Okay, so that is actually beyond what we did on Tuesday, or it's not Tuesday, on Thursday in period 2. That's about as far as we got in period 9 on Tuesday. So if you missed Tuesday, that's what we did Tuesday. All right, so the next video will be starting with number 5, and I will make that on the next video.